Okay, here's a review about the critical section problem. So what happens with the critical section problem is you have this critical data and you want to control access to this critical data and not come up with race conditions where the data becomes inconsistent or results don't happen the way you want. So the idea is that each process has a way to enter into the critical section, and only one process should be in there manipulating the data for the critical section at a time, and when they're done, they will exit. All right, so here's an example using this is a set of airplane seats. So just say, for example, all the processes are there and they can go and book an airplane seat. So let's just say that P1 is in there and P1 decides that they really like this seat right here. Doesn't have anyone next to them, so P1 books this seat right here. But before P1 has since there's no way to control how many processes are in there getting their seats, before P1 has a chance to even set the flag that that seat was booked, P2 goes in there and picks that seat. And then even before P1 or P2 have the possibility to set the flag that that seat has been booked, P3 goes in there and takes a look and says, oh, I'd like that seat. So you can see what can happen if you don't have any controls on how the processes are going to access this data and manipulate and change this data. All right, so if you had an entry section and an exit section, basically what you would do is only one process would be able to go in there. So for example, P3, since I'm on red here, P3 would hit the entry code right here. Whatever it is, if it's a lock or it's a semaphore or whatever, P3 would hit the entry code and ask for permission. And there were no other processes in there picking their seat or anything, so P3 would be in here picking the seat. And then if another process were to come along, say P1 comes along and would like to go and pick a seat, P1 would come here to the entry code and would ask permission, and it would find that the critical section is not available because there is another process in there. Meanwhile, P3 is in there, and P3 goes and finds the seat, books the seat, and after that seat is booked, sets the flag that that seat has now been booked, and then P3 will then run the exit. And when P3 runs the exit, then whichever process was waiting to enter will be able to go in and enter. And that would depend on a lot of different factors, whether you have those processes who are waiting to enter, if they are busy waiting. So then that would be the next one that checks, or they might be blocked and queue up. So even if now P3 is done and has exited, so now we're going to have P1 in there, so P1 will go in there and check, and P3 is done and P3 is exited. So now if any of the other processes like P4 or P5 come along, say P5 now comes along, P1 is already in there, P5 comes along, P5 would then be blocked out. So that's just the very basic idea of the critical section problem and how you control access to the critical section problem. And we already discussed there's the Peterson solution, which is a very simple solution that works for two processes. There's hardware solutions, test and set and swap, and different ways to lock. And there's another software solution called Semaphores, and Semaphores do the same thing, only they use procedures, wait and signal. So let's remember what wait does. Wait has the process wait if the semaphore is less than 1 or a 0, and has the process decrement and own the critical section if the semaphore is greater than 0. So it's very simple. This is a busy waiting type of semaphore. The process that's waiting is going to wait busy, checking and checking and checking, But there is also a complex semaphore in which the process will, which is in another video you can watch, an animation of that. So let's go back. So here, this would be the same thing. Whichever process runs the wait. So I've got this yellow color here. So we do P5. P5 comes here and runs the wait. And so the wait says that if S is 0, which S is 1 because it's been initialized to 1, then P5 will now change S to 0. P5 will be in here and will be booking the seat. And while P5 is booking the seat, if any other, oops, P5 is in here booking the seat. So P5 basically owns the critical section and no other processes can get in there because now the value of the semaphore is 0. So if P3 or P2 or P1, if any of them were to come here and run their wait, then what would happen is they would have to sit there and wait. So P1 could come along. P5 is already in there. P1 could come along. We could also have P3 come along here. And they're both sitting there waiting because P5 is in there finding the seat and then picking the seat, setting the flag that the seat has been booked, and then when P5 is done, P5 will then signal and leave. So P5 will be out of there, and the semaphore will then change the signal increments, and the semaphore will then change back to a 1. So now that the semaphore is back to a 1, if this is a busy waiting situation, which means they're taking up CPU cycles in order to check, whichever one runs the wait first will be the next one to go in there and own the critical section. And we'll block the other ones out. So just to review the wait, this is a semaphore with a wait and signal, and this does have busy waiting.